Okay, hello everyone. Welcome back to the Colchin seminar in differential algebra. Today we have Andrea Pulita speaking about exponents for irregular differential modules, a Tannakian approach to the theory of exponents. Thank you very much for your presentation.
Thanks to you, Daniel. Good morning to everyone. So allow me to begin by thanking the organizer for the kind invitation to speak at the Colchin seminar. It's a real pleasure, actually, to have the opportunity to share some recent work with such an international audience. My talk is about the theory of exponents of differential model, and I'm going to discuss how the Tannakian framework can be used to extend the classical notion of exponents to the case of irregular differential equations. So the talk is divided in three parts. The first part consists in giving motivation, explaining what I want to do. And actually, this allows me also to remind a part of the classical theory of differential equations over a field of formal power series. In the second part, I will enter in the subject of Tannakian groups, and I actually end with the third part in which I finally define the exponents. Okay, let me begin with the first part. The topic concerns linear homogeneous differential equations in one variable t, okay, and their classification. So a linear differential equation is something like this that you probably know very well. And in this particular case, I'm restricting myself to the case where the coefficients gi are formal power series. So for such kind of equations, we have a theorem by Turretin that tells us that we have a basis of solutions having this form. There's an exponential of a matrix. So this will be clearer in a moment. Okay, this is just an introduction. The exponential of a matrix Q, which is diagonal and has in the diagonal some coefficients which are polynomials in the t to the power negative of 1 over m for certain integer m. And then we have a factor t to the a. A is a matrix and possibly not diagonalizable. Okay, and then we have the product with a certain formal power series f hat. Okay, this system is regular when we don't have exponentials, so q is 0. And in this case, you can prove that the exponents are the eigenvalues of that matrix A. Okay, surprisingly enough, despite this explicit expression given by the theorem of Turretin, at the moment it's not possible to define exponents for any differential equation, even though the subject actually is very old. And the reason is that this product, t to the a times f, is not unique, actually, in this decomposition. This decomposition is not unique. So, for example, you might have in f hat some power of t that can be extracted from f hat and added to t to the a. So you see the matrix A is not unique in this expression. So, and I think it's relatively tricky to extract from this a reasonable information about the exponent. It is possible, but it's much convenient to use the theory of Tannakian groups. Maybe in the end this will be clearer. So let me fix some notation. I consider for simplicity an algebraically closed field K of characteristic 0. And if you have a ring R together with the derivation, then a differential module over this ring is a finite free module over R together with a connection, which is a map, which is a k-linear map satisfying the Leibniz rule. Okay, the object of this talk is the classification of those objects when R is a field of power series with coefficients in K. So maps between differential models are linear maps commuting with the connection. And these form a category of object whose nature is relatively algebraic, as you will see, even though the topic is differential. And I call this category D mod R. So if you consider a basis of your model, the connection, so elements of the model are now vectors, and the connection is given by the difference between the derivative of every coefficient of your vector minus a certain matrix multiplied by the vector. This matrix is completely determined by the connection and is called the matrix of the connection. Okay, so from this you can make a link with system of differential equations by saying that the solutions of the system are actually the kernel of the connection. And so as well as linear maps are described by, so encodes the deformation of system of linear equations, differential model are algebraic structure encoding the information of differential systems. So every system like that produce a differential model, and the point is that two different bases of that model may comes from two, so may have two different matrices, and hence two different systems. And it is one of the question is that, is there any canonical form of my system in which, for example, I can express my solution in a very easy way, such as the way suggested by the theorem of Turretin. Okay, so we want to find, so we want to classify differential model. This amounts to classify differential model. So what's the link between differential equations and differential models? If you have an equation like that, so there's a way to associate to the equation a model. So the equation has order n, and I think everybody has seen once this in the life. There's a way to obtain a first order system by considering the companion matrix. And reciprocally, if you have a solution to this system, this always comes from a solution of the equation. When the matrix is in companion form like that, this means that the model is of a special kind called cyclic. And there's a theorem of the Ligne that says that if R is a field, every differential model is actually cyclic. So every differential model has a basis in which the connection has this form. Unfortunately, this is not true for every ring, and this is a specific, so a true problem for p-adic differential equation, which is my topic. In p-adic, we don't have a cyclic basis, but we are lucky because we are speaking today about formal power series, so there is a cyclic basis. So let me remind what is an exponent for a model of this type over a field of power series. Let me first begin with a differential equation. So classically, you say that a number A is an exponent of the equation if the equation has a solution of this form, t to the power A times possibly a function, a power series f. In fact, in terms of differential model, this means that the model has a submodel which is isomorphic through a very simple model of this form. So associated with a very simple differential equation of this type, y prime equal to a over t times y. And the solution of such an easy equation is t, just t to the a. Okay. And then now you have to be careful because there are two distinct definitions for the equation and for the model. So the exponents of an equation are precise numbers because the equation is cannot be moved into another equation, so that there's no base change allowed. So, but as I said, for a model, you have several systems producing the same model. So the exponents are uniquely determined modulo addition of an integer. So they are actually elements in the quotient k divided by z, k plus. And this is because when you two models associated with the equation EA, so I mean with two different equations EA and EA prime are isomorphic if and only if A and A prime differs by an integer. Now, from now on, I'm speaking about models. So forget the definition of the definition for the equations. So exponents would be always elements in these quotients k over z. Now, what is a regular singular model? Well, it is a model. This is a convenient definition for us. It's a differential model over the field of power series in which you have a Jordan-Holder sequence of submodels, sub-differential models, in which every quotient, mi divided by mi minus 1, is one-dimensional and isomorphic to a convenient differential model of the form M of EA. Of course, the number A depends on the index I. You might have several rank 1 model of this form appearing in this list. So you have a list of rank 1 models, and they are associated with some exponents, A1 to AR, where R is the dimension of M. And this multiset is called the exponent multiset of your model. And the theorem of Jordan-Holder that tells you that if you have two different chains of submodels like that, they produce actually the same subquotients. So this list of rank 1 subquotient is actually intrinsic in M. And so this definition is well defined. Now, they satisfy some properties with respect, for example, to exact sequences. If you have an exact sequence like that, the exponent multiset of the middle is the union of the multisets of n and m, so of the exponent of the right and on the left. And the dual, the exponent of the dual is the negative of the exponent of m. The exponent of the tensor product is given by the sums of the exponents of m and n. And the exponent of the home differential model is given by the differences. So we have such nice properties. And the problem of today is the fact that we have a satisfactory definition for regular singular differential models. But yes.
Oh, could you show the previous slide again? Yeah, didn't you have two different formulas for the exponential of the tensor product? Oh, sorry, I read it wrong. You're right. Okay, one is a sum, the other is a tensor product. Okay, thank you. Thank you.
No problem.
Okay.
Thanks to you. So we want to extend this definition to irregular one. So the precise aim is the following. If we have a differential module of rank R, we want the exponent multiset, we want to find a multiset consisting of exactly R elements, A1, AR, in the quotient K over Z. And of course, we want this multiset to be an invariant by isomorphisms of differential models. And we want it to be compatible with direct sum, tensor product, and internal arms, as well as the exponent of regular singular model is. Okay, so at the moment it's not possible, as I said. So in order to give some motivation why exponents are important, so they are useful to classify regular differential models and the monodromy representations associated with differential models. And then it's also a necessary tool to detect when a differential model has algebraic solutions, because t to the a is an algebraic function only when the exponent a is rational. And allow me to say that in p-adic, there's a notion of p-adic exponents, which is a crucial condition for in order to have a finite dimensionality of the rank homology. If you want, I can tell a word in the end about p-adic situation. Okay. Now, what about irregular model then? If you have any differential model over the field of power series, it is possible to attach to this model some numbers called slopes. So if the model has rank n, for me, it has exactly n slopes. Maybe a given slope appears several times in this sequence. And allow me to say that such slopes are explicitly readable in a cyclic base. So if you consider an equation that produces your model, then the equation has some coefficient gi, and those slopes are essentially as related with the valuation, the t-adic valuation of the gi. So you place in a plane some points whose coordinates are I comma negative of valuation of gi, and then you consider a certain convex hull of those points, and the slope of the polygon that you find are those numbers, S1, Sn, modulo normalization. Actually, there are several possible normalization. This is why I don't want to be explicit on that. It's only important for us to know that those numbers are explicit. And this is another difference with the p-adic word, because they are not explicitly written in any. So we don't have a cyclic base, and we don't have an explicit way to read them in any matrix of the connection. But they exist in some context in p-adic. Anyway, we say that the model is pure if all the slopes coincide, so there is only one slope, and there is a theorem that tells you that every differential module can be decomposed into a direct sum of modules which are pure of slope S. And then a second part of possibly the same theorem, which is another characterization of regular differential module, and tells you that M is regular if and only if the slope is 0. So this is a way to read immediately in the coefficients of your equation whether the model is regular or not. So the polygon has to have is flat with only one slope equal to 0. Okay, now I would like to give you an example because this may be important in the rest of the talk. The one-dimensional differential model associated with first order differential equation is trivial if the valuation of your matrix of the connection is greater than or equal to 1. It is regular singular if the valuation of G is exactly equal to 0. Yes, it's greater than 0. Or if the valuation is negative, then the slope is exactly equal to the negative of the valuation, the slope of this model. It is also called, the slope in this case, it's also called the irregularity. So in this case, the irregularity is the valuation of G. So, sorry, the negative of the valuation. Well, we have a complete classification of rank 1 objects, rank 1 models. In fact, we can, with a base change, we can suppress the coefficients AI, which are with I positive. A0 is uniquely is uniquely determined modulo Z, and the other coefficients AI with I negative are unique, are really unique in any so you cannot move them with any base change. So the pair given by this polynomial, which is part of our matrix of connection, and the image of A0, sorry, the image of A0 in the quotient K over Z. So this pair classify completely the isomorphism class of rank 1 models. So this is really important when I want to define. So as you can see, A0 exists. The residue can be considered as an exponent for this irregular differential model. So this will be the definition that I will repeat when I'm going to define exponents for irregular models. So let me recall the theorem of Turretin. Then there is a way to so if I ramify my variable t, and I pass from t to the power 1 over n, then when I consider the scalar extension to this new field, the theorem says that there is a value of n such that my model has a Jordan-Holder sequence of rank 1 with rank 1 subquotient, every subquotient at dimension 1. So I can reduce myself in many situations to the rank 1 case. So the slopes of M are actually the collection of the slopes of the subquotients and they coincide with the slope of m multiplied by n. And in particular, the slope 0 is coherent with this step, the scalar extension. So you consider the extension of the slope 0 part of m, and this coincides with the slope 0 of the extension of n. Okay, and then the exponents are, however, multiplied by n in this process. And this is a problem because some exponent is killed. So if you have a rational exponent in your model, so if m has a regular part, and the exponents in that regular part, some of the exponents in that regular part are rational with a denominator n, then when you pass to when you consider the scalar extension, they are multiplied by n, so they become integer, so they go to 0 in the quotient. And so this is why actually Turretin cannot be really used to define exponent. Well, I will say a word in a second about that. So allow me to recall that this definition, so the regular differential equations have a long story. So I give here some definitions. In the irregular case, there exists a definition for equations due to Daniel Bertrand and his student Edouard Corel, which concern differential equation not model. So they provide precise elements in K, but actually they use Turretin theorem, as I said. And there's another definition in the book by Andrea and Baldassari, again using Turretin. And as far as I can understand, the two definitions should coincide if you consider the module associated to the equation. Now, the problem, as I said, is that the extension to this new field kills some rational exponents. Okay, because exponents are multiplied by n. So the idea of those authors is to consider the exponent after extension, and it's not really possible, in my opinion, to divide it. So they suggest that it's possible to divide it by n, but this division is not canonical. And so what is canonical here is that the exponents defined in that way are elements in K over Q. And then, for example, in p-adic, we have a problem because in certain situation, all the exponents are rational, so you don't have any more exponents. It's also a problem if you want to find, for example, if you have a regular model, you want to split the model according to the exponents. You want to have a kind of Jordan decomposition. But if all rational exponents coincide, so if they are all equal in the definitions, you cannot separate them. So we really want to have exponents as elements in K divided by Z in order to agree with the classical definition where M is regular. And we also want to have a complete multiset formed by dimension M elements. Okay. Okay. So give me another second to explain another motivation. If M is completely irregular, so the regular part of M is 0, I might consider the module M tensor M dual, which is isomorphic to end of M. And this may have a non-trivial regular part Actually, it can be also regular, entirely regular. And the exponents of this regular part of the endomorphism are supposed to be the differences of the exponents of M. But M itself has the empty set as exponents, which is not natural at all. And in fact, for a general differential model, and M has always a non-trivial regular part because it has the identity which generates the trivial submodel. So this and the other examples convinced me that actually every differential model should have a complete set of exponents. So complete means that I want to have R, a multiset formed by R elements, where R is the dimension of M. So now I would like to see this what happens with the Tannakian approach. The theory classifying the isomorphic classes of slope zero models is similar to the Jordan classification, and there's a reason for that, because you can prove that the regular, so reg is the full subcategory formed by regular differential model, and this is a category which is isomorphic to a finite representation of the group Z. So K, so these are finite dimensional vector spaces together with an action of the group Z. Okay. So which amount to say, oh, there's a mistake here, sorry. There's amount to say that you have a vector space, a finite dimensional vector space, together with one individual automorphism, so a bijective linear map. In this case, the relation between the eigenvalue of that linear map and the exponents is that the exponents corresponds to eigenvalues via an exponential map. Okay, because you actually have such an exponential in an abstract way. Oh my God, something happened. Sorry. Oh, sorry. Okay, I was here. So exponent corresponds to eigenvalues. So the Tannakian group of this is then isomorphic to the algebraic envelope of Z. And this algebraic envelope can be described as GA times another group still called Z, which is the dual of this quotient K over Z. In terms of differential Galois theory, this is the differential Galois group of the extension of K of T obtained by adding the symbols T to the power A. So this form a differential field. And if you consider the differential Galois group, what you obtain is the dual of this K over Z. Z is an abelian group, and the representation of Z are completely given by the multiset of the exponents, are determined by this multiset. So the slogan is that when you have a differential equation of this form, the solution is T to the A, oh my God, and the Tannakian group is Z, and its dual is K over integer. Oh. Now, let me come back to the whole category of differential model, and let me call G the pro-algebraic group, which is the Tannakian group of this category. Now, it is known that this group it fits into an exact sequence in that way. So it has a Z, the algebraic envelope of Z as a quotient because this category has a subcategory of regular model. And so the kernel of this map is a pro-torus, and G is a semi-direct product, actually, of these two abelian groups. This theorem constitutes a way to completely classify the objects. So gives a description of the group. So and we would like to extract from this decomposition the definition of exponents. So if you want, we can describe the pro-torus. So as you remember, rank 1 object in the category are determined by the negative part of the formal power series, which is the matrix of the connection, and the residue of the matrix of the connection. And then the Picard group of the category, which is the class, so isomorphic classes of rank 1 models under tensor product, is a group isomorphic to this one, to the group polynomials in the negative power of t without constant term plus k over z. Now the group is abelian, and the dual of this group is given by homomorphism to, so it's given by this union of polynomials in t minus 1 ramified. Okay, and so the slogan here is that if you have an irregular differential equation with q in q, then the solution is an exponential, and the group is tau, and the critical group is q. Now, with this in mind, I would like to define exponents for irregular model. So in rank 1, as I told you before, it is kind of natural to consider the residue, which we know to be an invariant by base change of the model. So we call this residue the exponent of my model. And then this is possible because the residue map is well defined in the Picard group. And this residue map corresponds precisely to another map in the reverse sense at the level of Tannakian groups. I will show you in a moment. The main idea that you might have at this point is that to use Turretin theorem plus Galois descent. So the Galois group should somehow gives you a way to remind or a datum that can distinct different kind of exponents after ramification. But and then that is possible actually, but it's quite involved to be explicitly expressed. So it's much so the approach with Tannakian group is much more direct and simple, as you will see in a moment. So remember that regular model have a group which is essentially Z, and the whole category of differential model has a group G. Okay, so we start from a representation of G. When we consider a differential model, this can be seen as a representation of G. And so if we want to attach to this model a multiset of exponents, as you have seen, the exponents determine a representation of Z, a certain representation of Z. So we would like to obtain from this representation of G another representation of Z. And but the point is that Z is, oh, the semi-direct product is inverse here, sorry. So we would like to obtain in a canonical way a functor going from representation of G to representation of Z. But the problem, oh, what's going on here? Oh, nothing works anymore. Okay. So the problem is that when you have a representation of G, there's no canonical way to obtain a representation of Z, but there is a non-canonical one. So, for example, you can consider a section of Z into G. And then you might define the functor R just as the restriction to the image of C in G, which is a copy of Z in G. So this is a restriction operation. And then let me give you the recipe to define exponents. So you choose a non-canonical session, and I want it to be compatible with the residue map. In a moment, you will see what I mean by that. So I'm going to define, so I'm considering a differential model. I think this differential model has a representation of G via the equivalence. Oh my God. So the restriction, so then I consider the restriction of this model to the image of S. This is now a representation of Z. And then by the equivalence, it is a regular differential model, which has a complete set of exponents. The dimension is, of course, preserved by this process. And I call this exponent Tannakian exponent associated with M. Now, it's an invariant by isomorphisms, of course, and it is compatible with everything, because if you think about it, it's just the restriction to a subgroup. So it's compatible with all the operation, tensor product, exact sequences, sums, duals, and everything. Okay, but the point is that we chose a section to define it. Is it intrinsic? Now, at least at the level of the abelianized groups, this is the dual of the abelianized of G, this Picard group. And this map is what we choose to be the residue map, was the map giving us the exponent. And actually, if you think about it, there are several possible maps going from this group to K divided by Z. The residue map is not the only one, so there's no canonical choice. We choose it to be canonical, the residue map. By duality, this gives us actually a canonical distinguished section associated with the residue. And then again here, we might have many sections from Z to G lifting this canonical residue section. And the theorem is that whatever section you choose lifting residue, if you follow the previous recipe, you will find the same model, the same regular model. And that's the theorem we have proved. And so the result, in particular, the resulting exponent multiset is the same in the two cases. And that is why exponents are well defined. Of course, you can translate this group theoretical, so the existence of this section, sorry, come back to the section. So you want a section here. Choosing a section means, if I come back to the very beginning of my talk, when I expressed the solution as an exponential of a matrix and t to the a, the choice of such a section corresponds in terms of Galois theory to finding in a non-canonical way, actually, a field that you obtained from k of t by adding the exponentials, only the exponential and not the power of t. So this is possible, but there are several non-canonical ways to do that. So what I have just told you in terms of group can be translated in differential Galois theory by saying that you choose a non-canonical field of those, and then you take the scalar extension to that field, which correspond to the restriction to the image of this subgroup. Then you have a regular model for which you can define exponents. And then this is independent on the choice of the field extension. My talk actually ends here. If you have questions.
Thank you very much, Andrea, for this very nice talk. Are there questions or remarks? Please just unmute yourself or write in the chat. So previously you recalled that with the original exponents you can decompose a module into a direct sum, right? So did you have that corollary here as well?
No. Unfortunately, this is not possible. It is not possible. There are, for example, irregular modules which are simple as differential models, so they don't have submodules, and so you cannot hope to have a decomposition. Anyway, we have a set of elements that are useful to classify the irregular model. For example, two irregular models are isomorphic, so cannot be isomorphic if they don't have the same exponent multiset. So this is just a numerical invariant attached to the model.
Okay, thank you. Yeah, very interesting. Are there other questions or remarks, please? Have a look to the chat. Nothing there. Okay, if this doesn't seem to be the case, we thank Andrea again. There is a question. Okay, yes.
How does the multi-exponent depends on G, the capital G, for the module, for the differential module?
So I mean the matrix G or the group G?
The group G.
Depends on G. Well, G is here the Tannakian group of the category. So G contains, I mean, differential models are the representations of G. And they, I mean, if I can interpret your question, is that if you have the representation of G, you should restrict it to the image of a section of Z in G, and then you obtain, I mean, from the entire representation associated to every element of G1 matrix, right? So somehow this tells you that only one of those matrices produces, it's the matrix. So I'm thinking about this. So I come back. So allow me to be more explicit. So we have this exact sequence, and a representation of G is a map from G to the automorphism of V, where V is a vector space. So every element of G goes into a matrix. Well, this contains the information of the exponent in the following sense. If you consider the element 1 of Z and you lift it into an element of G in any way, okay? So you consider an element of G whose image is 1, then the matrix associated to that element of G is a matrix that contains the exponent multiset. So the eigenvalues of that matrix are the exponentials of the exponents. So if you have the representation entirely, you can compute the exponent in that way.
Okay.
So you just watch one element and its matrix. You take the eigenvalues and you have the set of exponents by considering logarithms.
Okay. Well, so all these calculation of these multi exponent, do you have an example, simple enough to show, say, just rank 2 maybe, or?
Well, no, not here, not with the slides, unfortunately. But I mean, if you, well, the example are not really complicated once you use Turretin theorem. So with Turretin theorem, I mean, what I wanted to tell you here is that the first idea was to consider to pass to this extension and then computing Galois, so use the Galois group. And then actually the first thing I've done was to actually make explicit this Galois action. And I wrote several pages of tricky computation to understand that in the end the operation was very simple. So it is possible to write down explicit examples, but I don't have one here to show you, unfortunately. Sorry about that.
All right, thank you.
Are there further questions or remarks?
If you don't mind, I will
Yeah,
just
please. Yeah, please.
make a comment on a typo. When you write D with a minus sign modulo the power series, I mean the D minus the module category of you actually mean differential module, right? So
Yes.
please don't use the minus sign, use a hyphen.
Okay, thank you.
Sorry about that. Okay.
Further questions for Andrea or comments?
That's a very nice talk. Thank you very much.
Thanks to you for the questions.
Okay, it seems everyone is happy. So thank you again for this very nice talk, and see you all next week.